All right, how is everybody doing today? Gauss's law. Yeah, okay. You're supposed to cheer and be like, Gauss's law. It's fantastic. It's confusing. Yes. Last Thursday, it's a little heavy, it's a little hard. I know things are a little difficult. Because of that, I'm going to make you work a little bit today. Meaning, I know that sounds bad. It's like, it's hard. Now I'm going to make you work, like two bad things. To try to help you understand in a little more detail, we are doing some more examples. Before the class is out today, though, I'm going to give you another example or two to work in class. So we'll take a little time so you'll have a chance to ask questions, work together a little bit. I know that you're putting off your homework, even though you really need to not be. So I'm hoping to push you a little bit now to start practicing some. So we'll do that by doing it in class a little bit. Also, I got a little bit of feedback regarding the video lecture from last week when I had to do a video lecture, saying that like a little more of that could be handy, especially if you need to like re-listen to an explanation of something. So I'm going to do a little experimentation starting today to see if I can get a decent recording without too much extra stuff in my workflow. I clearly can't just go home every night and redo the lecture again. So there's just no time for that. I'm going to see what happens. I'm going to see if the computer can capture that reasonably well. I already tried doing it by doing a screen capture on here while talking. It turns out you can't project and record the screen at the exact same time. Some sort of technical limitation. So I'm going to try this. We'll see if the audio is getting me over there. Sadly, you might on the video occasionally see my head walk by. Ah, there I am. So you can watch that later. So we'll just kind of see what happens and whether or not we can pull that off and find out if it's useful for anybody. If I upload them and there's like no views, then I'll be like, well, I'm not going to waste my time. But, you know, we'll see what happens. Maybe it'll be of use. Let's see. So let's jump back into these Gauss's law problems. We did two. The two that we've done so far were both problems that involve something spherical, which means I used a spherical Gaussian surface to help me solve the problem. What I want to do to sort of wrap up the examples that I'm going to do is actually two more on this slide. The one that's described there is actually the fourth one that I wanted to do, so let me renumber these. I'm actually going to put that back and say that that is 4. There we go. So that's 4. And we're going to do this one sort of over here on the right-hand side. And before that, I want to do number 3, which is also going to use a cylinder or a box. Well, for this one, a cylinder only will work, it turns out. And let me tell you what this problem looks like. It is a very long, think so long it might as well be infinite, okay? A very long, straight wire with a positive charge density. Positive charge density, and we'll call that lambda. Long straight wire with a positive charge density lambda. Also, if it gets a little too chilly on this side of the room, or this starts just waving so much it makes you a little ill, let me know and I'll close that window. I already noticed it was billowing quite a bit, so if that drives you a little insane, just say the word. A cylinder, we're going to have a very long straight wire with positive charge density lambda. So, what I mean by that is literally we're just going to say there is a wire that basically has no real thickness to it that we can discern. We're going to say that it's really, really thin and small, such that when I think about the charges that are lined up, it's almost like they're all in a row, like they're in one dimension. So you might think of these charges like this. Here we go. Positive charges all along this wire. So we're not going to be able to go inside the wire like we did with those previous examples where we like had an inside answer and an outside answer. This is so narrow and thin that we're just going to try to find something about the electric field outside. So first of all, if I just drop positive charge anywhere, let's say here to begin with, which direction will it be pushed? It's going to try to get away from all those positive charges. If I put it in the front, which way is it going to be pushed? Like straight away from all those positive charges. If I put it behind, it would get pushed away from all the positive charges. If I put a positive charge on top, it gets pushed up, right? So you could imagine an electric field that sort of looks like this in all directions, radially around this wire. Electric field everywhere. So in other words, if I were looking at the wire sort of end on, right, and I could just see like the end with one of my positive charges, we're imagining that there's an electric field that points in all directions out from the wire on all sides. So this is an end view of the wire. And I should label that electric field too. There we go, electric field, electric field. So we're going to try to find the value of, or rather an equation or formula or an expression that tells us the electric field some distance away from the wire on any side. We're going to go to some distance r away from the wire and find the electric field. So to do that, I'm going to set up a Gaussian surface that is a cylinder. And this is where things artistically get a little difficult. But hopefully you can sort of get the idea. Okay? I'm putting a cylinder that's imaginary around the wire. And you can imagine the wire passing sort of straight through the center of the cylinder. Again, if we look at it end on, essentially it's just a circle if we're looking at it from the end. Okay? Can everybody at least partially understand what I've drawn? Sort of, okay, we got it. So let's see, what was I using previously? So we're going to say that this has a radius r. We use a capital R for that. And if you think about it, my electric field is passing through this imaginary surface, this Gaussian surface, this cylinder. Some of it is passing through the walls of the cylinder, right? The rounded part on the side of the cylinder. Some of it may or may not be coming out the ends of the cylinder. There's 3 different surface areas on a cylinder. Unlike a sphere, just one big surface area, here I've got 2 end caps that are circles, and then I've got this rectangle that wraps around the side of the cylinder. We're going to look at the flux that passes through all parts of those, okay? So in other words, when we write out Gauss's law, so let's start with just our overall equation. It's E dot dA is equal to Q enclosed over epsilon naught. We are essentially going to have 3 parts on the left-hand side because I've got 3 different areas to deal with, okay? So once you see what it looks like, I'm going to do a lot of work to show you how simple it actually is. So the next time you do something like this, you might not need to draw all this much. So I'm going to say E dot dA for the side of the cylinder plus E dot dA for one end of the cylinder plus E dot dA for the other end of the cylinder. I don't know what happened to that last cylinder. It just kind of turned into I got kind of lost in the middle there. Did you get the idea? That's the left-hand side of the equation simply because my cylinder has 3 different surfaces that I need to consider how much electric field is passing through, okay? On the right-hand side, we still have Q enclosed over epsilon naught. So let's talk about this circle on the one end of the cylinder. How much electric field is passing through that end? None. Yeah, none is the answer. I'm going to pretend all of a sudden that this is the cylinder. I'm hoping the lid is on there okay, right? You can imagine if the electric field is sort of going past the end, it's not actually going through that circle. Much like when we talked about if I put the iPad like this and the electric field is going this way, it just sort of flows past it, but doesn't actually pass through that surface. So there is no flux passing through that end. No flux. I don't know why I keep writing the wrong letters. And you might quickly arrive at the idea that there's none passing through the other end either. So it's also zero. The key that I want to point out is that you have to think about all of the surface. Here it's broken into 3 different parts. So any flux that I have passes through this side wall of the cylinder. Okay? So let's see. Let's bring this down. And we're going to say that the electric field will be constant a given distance from that. So I'm going to pull that out of the integral. And this closed surface integral of dA is just going to be the surface area of the side of the cylinder. We'll put a big equals and put Q enclosed over epsilon naught. We're getting close to an answer here, believe it or not. What's the equation for the surface area of the side of the cylinder? It's close. That's one of the dimensions. It's 2 pi r times the length, right? If you unwrap the cylinder, it's a rectangle. And the length to one side is the circumference of the circle. And then I have the length of the rectangle as well, or the length of the cylinder. So this side is going to be E times 2 pi r L. That's the surface area of the side of the cylinder. The circumference is one dimension. The length of the cylinder is the other dimension. So let's go ahead and write in L here for the length of the cylinder. There we go. Now remember, going back up here to this positive charge density, this linear charge density is Q over L. Okay, linear charge density is represented by Q over L, which would also be Q enclosed over L enclosed. You can see that I can rearrange that and substitute in for Q enclosed, right? So this Q enclosed, whoops, we don't want to put that up there, is going to become lambda times L enclosed. And let's keep the epsilon naught in the denominator. Now notice, this L that's on the left-hand side, that's the length of my Gaussian surface. This L on the right side, L enclosed, well, the enclosed length is also the length of the Gaussian surface. Those are the same thing. So let's cancel them out. Okay, we describe them a little differently, but they're describing the exact same length. Which means that we're basically done. We can rearrange that for E, and now we have lambda over 2 pi epsilon naught r. If you know the charge density in your line of charge and you go to a certain distance, you can find the value of the electric field at that distance away from that charge distribution. I think, on a whole, that was a little easier than some of the other ones we did last week. Maybe. Maybe. Just say yes. Maybe. Okay. We're going to do one more. But let me pause and see if anyone has questions about this one. Is there anything up there that's just bothering you a little bit? You're thinking, the whole screen bothers me. I understand. It's okay. We'll get there. Have you started your homework? This is where I look out and I see people that are doing this. Like looking anywhere in front of the classroom. I get that. Also, checking WebAssign just before I came in here, I think 59 of you are registered out of the 80 or so that are in the class. So I am very much aware that, yes, 20 of you haven't even logged on and signed up and accessed it yet. Do it today. Got that? Otherwise, I will hunt you down and put your fingers on the keyboard and say, do things there. Okay, because that's about as much as I can threaten, really. Okay? So do that today. There have been some complaints of access codes not working. And if you bought the book previously, you're supposed to still have access if you bought it last semester for 220. So if anything's not working right, I need to know as soon as possible so we can get all that resolved, okay? So make sure you try and let me know if you have problems. And then, as soon as you get it resolved, work on the homework. Go buy a burrito, sit down, work on the homework, okay? Actually buy 4 burritos, 2 for you, 2 for a friend, and work together, okay? Sound good? 6 burritos is better, maybe? 3 for you, 3 for a friend? I don't know. Maybe an infinite supply of burritos until the homework is done. Just keep the burritos coming. Whatever it takes. Just get started on the homework, all right? I'm going to insert a slide here because it turns out that took more room than I thought it was going to. So let's see, add a page. And it's going to come out the wrong orientation, but it'll still get the job done for us. And we're going to do one more problem, and this will be the fastest one of them all. It was described on the previous page, but I'll write it here again. This is an infinite insulating plane of charge. We will say that it has surface charge density sigma for that. Surface charge density positive sigma. So, oh boy, here we go with the artistic troubles once again. Okay, plane of charge. Imagine an iPad, okay? Infinitely small perhaps, such that instead of just having a line of charge, it's like a bunch of lines of charge all sort of lined up. So if we wanted to kind of like try to draw it with a little bit of perspective, right? It's just like a bunch of charge that's all evenly distributed on this plane. And we're going to say that it has essentially no thickness. I could look at it from either side and be like, look, plane of charge. And I could look at it from the other side and be like, look, plane of charge. But if I look at it from the side, there's almost nothing there, okay? So that's kind of a perspective view. It might be a little easier just to sort of rotate this around and imagine something that kind of looks like this, looking at it from the side. And all of a sudden you're thinking like, that looks a whole lot like what you just did. You just have to remember what's hiding behind it, right? I'm just showing you like the end of the iPad. There's actually a surface that's going into the screen. Got that? Okay, it's a plane this time, not a wire. So, again, if you were to imagine what happens to a positive charge, if I put a positive charge here, it's going to be like, yeah, run away. It's going to get pushed that way. If I put a positive charge on the other side, it's going to say, ah, run away. We can't really look at any other sides because, again, it's a plane. I can either be on this side or this side, and then it infinitely goes in all directions. I just can't draw an infinite plane because we would be here for a while, right? Infinite plane. Need a new page. Infinite plane. Need a new page. Infinite plane. And then you'd be like, eventually, like, that was an interesting class. He just drew an infinite plane. Lecture after lecture after lecture. We don't know what we learned, but it was an infinite plane. And then the semester would end, and I'd be like, you can't leave. The plane is not complete, and never will be. Infinite plane. Okay, never mind. Need to erase this recording already. It's embarrassing. We don't need things like this floating around for consumption. So anyway, electric field. We're saying that it's this way. It either points out to the right side or out to the left side. Or rather, it's pointing out both sides. Because anywhere I drop a positive charge on the left or the right, it just gets shoved away. So, here's what we're going to do to find the electric field this time. And here is where I have literally no ability to draw this, okay? So imagine a box, okay? Just maybe like a cube, a box, a little cube. And we're going to essentially take the box and, whoops, we're supposed to be drawing something imaginary, so it's dotted. And we're just going to stick that box right through the plane, okay? So it's like, there we go. We had a plane we're dealing with. And then I need a cube. I don't see any cubes of any type that's around here. Pretend this is a bottle of water that's a cube. Got that? Okay? We're taking the cube and just sticking it straight through the plane so that it, well, that would be disturbing if I just went, whoo, and stuck it straight through there. You get the idea, right? It's stuck through the plane. So while I can't really draw that, we took a box and stuck it through the plane. It's almost like we were making biscuits. Anybody like biscuits? Biscuits? Biscuits. I'm talking like breakfast biscuits, like you'd get like in the southeastern United States a lot. Like biscuits, like fluffy, you put sausage on it, you might even put gravy on it, you might throw a slab of egg in between the two, like biscuits, okay? Except we're making square biscuits. Like we had like one of those dough cutter thingies, you know, like you have dough and you're like, chink, you stick it in the dough. I don't know what I'm talking about anymore. You get the idea. Hopefully that's enough of a description. You can determine what's happening in that diagram, all right? So if I have a box, you can imagine the right side of the box has a square on it and there's electric field flowing through that square. The left side of the box has a square and there's electric field flowing through that. But of course, there's also like a top of the box and a front of the box and a bottom of the box and a back of the box. But electric field is just flowing past all of those sides. It's not actually flowing through those surfaces, okay? So I'm not gonna write down this equation again except with like 6 terms. I'm just going to tell you that we are gonna be dealing with kind of like what we had right here, right? 6 of these, 4 of them represent 4 of the sides of the box that have no flux passing through them. 2 of them represent the 2 ends of the box that the flux is actually passing through, okay? So we are going to just write something like, let's just say this. Let's write E dot dA, and we will say this is for one side, plus E dot dA for the other side. And maybe if you want to think about it, it's left and right. I'm going to draw a couple of arrows. We're going to say that this one represents that side, and this one represents that side. The other 4 sides are 0.
Are they just 0 because we're disregarding them? You said they went to 0?
They are 0 because that term, this E dot dA thing, is electric flux, which is a measure of how much field passes through. And for those other sides, it's just like going right past. It's in the same direction. It's parallel to those sides, so nothing goes through those surfaces. Okay? And on this side, Q enclosed over epsilon naught. And we're basically done. You're like, you just started this problem. I promise you, we're basically done. Watch what happens. E is just going to come out. It's constant, a set distance away from that plane. And then I've got, let's see, dA plus this other integral dA. I've got that twice. This is the area of one end, and this is the area of the other end. Keep it in mind that those ends are squares or rectangles, or technically they could be any shape you want them to be because they're about to cancel out. Okay, we'll just pretend they're squares, why not? And on this side we still have Q enclosed over epsilon naught. So, yeah, that's getting a little rough up there, isn't it? Just all you have to do is move your head exactly with what the sheet's doing, and then there's no relative motion between you and the sheet, and it'll be fine, right? Okay, I'm going to stop trying to do that. It's kind of a challenge, though. Watch it and see if you can like mimic exactly what it's doing. You know, it's kind of creepy and dumb, and I'm going to stop now. So let's see. If we have a surface charge density, we should start getting the idea of how to write the surface charge density. In this particular case, it is going to be sigma times the area enclosed, because remember this thing is equal to Q enclosed over A enclosed, and I just rearranged it. All right. If I'm dealing with a box, and if you want to think of it as a cube instead of just any old rectangular box, well then the left end of that is a square, the right end is a square, and the area that's enclosed by the box, you might imagine, is a little piece of this surface. Oh, that is like right here, like I've enclosed that much of the plane. And if I looked at it, it's a square. Yes, it's the biscuit that I cut out of the plane, okay, the square biscuit. So all the areas are exactly the same, which means I can go back down here to the bottom and write this as E times 2A. I'm just going to write area because it's an area, we understand that. And on the other side, I have sigma times the same area. Notice the areas cancel out. So it really didn't matter if it was a square or a circle or some kind of weird blob, because it turns out it just doesn't matter for the situation. And you can very quickly see that we have an answer that looks, ooh, I left out something. Do you see what I left out? I just lost a constant a couple lines back. Yeah, the epsilon just kind of went away. There we go. Let's keep that around. My apologies. This is just equal to sigma over 2 epsilon naught. Told you we were about done. You should at this point start to, like, it's hard. I get that it's hard, but you start to sort of see a trend in the way we think through the problem. And every one of them sort of works out a little bit different. There's a little twist to each one of them that's a little different. And the more you see, you start to kind of get a feel for how it's going to turn out. But the procedure is essentially the same for all of them, okay? You're going to start by thinking about which direction the electric field is going. Is there a shape that sort of fits the geometry of the problem, where at least on some surface, I'm going to have a constant value for the electric field, and maybe on some other parts of the surfaces, it's 0, okay? And then we're going to do something on the left-hand side where the area is constant, and we find a surface area. And on the other side, we're trying to figure out a way to either plug in how much charge is in this surface, or if I have a charge density, re-expressing that, seeing what cancels, and solve for E, okay? Yes, those were a lot of words. I said a lot of things there. I have 2 problems that I want to give you in a little bit, but not quite yet. We're going to end the class with those instead. Does anybody have any questions about what you see up here right now? Strange sound. Anybody? Anything? Just silence all around? Has anybody signed up for WebAssign since I've been talking? Yeah, okay. I thought there might be a couple few out there. More are going to do that, and that's good. That's fine. Get that done. I'm going to check the numbers again later. We'll see what we're up to. Okay, so let's go over to this slide. And actually, the next one I've already crossed out because it doesn't help us at all. We don't need to talk about that. So this is the last one I'm going to talk about. And it turns out what is on this slide sort of just brings together the last 2 chapters. We talked about electric fields and conductors in the last chapter. We basically said a few different things. First of all, the charges are sort of free to move around. So if I have a conductor, the electric field is perpendicular to a conductor, but also it can't be inside a conductor, okay? We can use Gauss's law to show that at least that last one is true. Electric field is 0 inside a conductor. So here we have 3 different random shaped conductors. Okay? So first of all, if we were to assume that there is no electric field inside this conductor, so we're going ahead and making this assumption, let's see what it tells us, okay? So notice they've drawn a Gaussian surface sort of just inside the edge of this conductor, okay? Meaning that when I write out E dot dA for this particular problem, like so, I know that if there's no electric field inside the surface, then there's no electric field like passing through my Gaussian surface, which means that this side is 0, which leads to this idea that the charge that I've enclosed has to be 0, which means if there's no electric field inside the conductor, then we also know that there is no Q inside the conductor. It is all on the surface. So it's like we assumed one of the things that we know to be true, mixed it with Gauss's law, and we get the other thing that was in our list of things about conductors and electric fields. All the charge has to live on the surface if there's no electric field inside. And a quick version of Gauss's law shows that, okay? On the other hand, if we had a conductor that like had a hole cut out of the middle, and again, it looks like someone cut a biscuit out of that conductor, just like a circular hole right in the middle of it, okay? Where's the charge? We think it's all on the outside, but you might be like, hey, there's a surface like inside that hole. Maybe it goes to all the surfaces on the conductor, including the little interior surface inside that hole. Well, keep in mind, once again, we know that the electric field has to be 0 inside the conductor, which means if you draw a Gaussian surface the way they did, and there's not a good way for me to point to this, a Gaussian surface here that is inside the conductor, you can see that those little green dashes are actually in the conductor itself. Well, I know that electric field can't be passing through that Gaussian surface. It has no option, which means that, well, there can't be any charge enclosed. There's no electric field passing through the dotted line. There's no charge enclosed, which means this interior surface, there is no charge here. Instead, when I drop charge, it all goes to the outside surface, all on the outside surface of the conductor. Okay? No electric field in a conductor leads to the idea of no charge enclosed by that Gaussian surface, which tells me that some of the charge doesn't run to the interior surface. It still gets as far away from each other as possible and goes to the outer surface of a conductor with a hole cut in it. Which brings me to this third one, which after we introduce the new chapter is going to lead to one of the problems that I want you to do. I'm going to give you kind of an intermediate sort of like relatively easy, but with a new idea and a new twist that I'm going to tell you about right here, okay? Notice what they did. They took a conductor. We're going to start with a conductor that's neutral. It has no charge on it, but then they drop a charge into the little hole inside the conductor, okay? Into that empty space that's inside the conductor. And then once again, try to figure out what happens with the charge, okay? So let's think about this just a little bit. Notice the way that they've drawn the charge. For whatever reason, they've decided, hey, I've got a bunch of negative charges on the inside of that little surface now, and now a bunch of positive charges on the outside, okay? Let's see if we can figure out why they did that. Keep in mind, if I draw the Gaussian surface here where they did in the conductor, the electric field there has to be 0 because it's inside of a conductor. That means that the charge enclosed has to be 0 inside that Gaussian surface. If there is physically a charge that's here, I've got a little bit of a problem. It almost seems like a contradiction all of a sudden. I can't have any charge inside this Gaussian surface because there can't be any electric field passing through that Gaussian surface. So if there is physically a positive charge here, it has to be canceled out by some other charges. So those negatives that they've drawn literally exist, and I don't really like where they've drawn them, sort of just on that interior surface, such that it's inside my Gaussian surface, the dotted line. That negative charge is equal to a total of negative Q, so that now plus Q minus Q, there's still zero net charge enclosed inside the Gaussian surface. Gauss's law tells me that essentially by putting physically a positive charge in the inside, it attracts a bunch of negative charge to it, just enough to cancel it out, okay? If I pull a bunch of negative charge to the inside, that means it had to come from somewhere else, and that leaves a net positive charge elsewhere. So all of these positives that they've drawn on the exterior surface, they all must add up to be positive Q, okay? Putting that positive Q in the inside drew enough electrons to it to cancel it out, and that left a deficit of electrons somewhere else. So keep in mind, the conductor started with no net charge. Putting a charge in the middle made the charges redistribute themselves to make Gauss's law work out, okay? Yeah.
So did the conductor become polarized?
You can think of it as polarized in a way. It's kind of like, I don't know, like radially polarized, like there's charge on the inside, charge on the outside. But yeah, you can think of it like that. That's the end of chapter 23. Or is this 24? I'm confused now. 23?
23.
Are you sure? 23? Okay, I believe you. We're going to come back to Gauss's law in about 15 minutes. Can you listen to me for 15 more minutes? That's a lot of people looking away again. It's like, I don't know. I don't want him to see my eyes. I don't know if I can do it. I can't do it. 15 minutes. A long time. 15 minutes. All of you stand up. Just stand up. You can do it. Just stand up. Oh, you're just going to leave. I say stand up. He's like, I'm not here. That's fine. Okay, I don't like this. There's something intimidating when you all stand up. Because now all of a sudden, even though I'm standing on a step, I feel short. It's like, and now if I like walk down here, I'm like, so many of you are bigger than I am. Now I just want to run back up here again. So before you sit down, we're going to try something. How many of you are sleepy right now? Even though you stood up. Yeah, a lot of you are sleepy. I heard that laughter makes you wake up. Even if you fake it. So in other words, right now, all of you just fake like you're laughing. And if you're, even the faking will turn real if you fake it hard enough. Are you ready?
No.
No? Like we're just like belly laugh, just roll like this is the most hilarious thing ever. And by the time we sit back down, we're all going to be relatively awake enough to listen for like 12 minutes is what I'll have left at that point. So are you ready? Don't make me do this by myself. You laughed there, but that was almost genuine. Ready? We're going to laugh loudly and fakely. Okay? And go. Help me. That was sad. So I want you to remember this, and we're going to do it again, and we're going to fake better next time. No? Sit down. It helps a little bit. Who's still sleepy? Okay, yeah, that's fine. I know. I'm chronically sleepy. My wife thinks I might have narcolepsy, but like of a type where I don't just like pass out all of a sudden. It's just more of a chronic tiredness in that if you just give me a minute, I'll pass out just like at any moment. So I don't know. I should be tested. Sounds like I'd get to do a sleep study. That sounds like the best, right? Like the doctor says, come in and go to sleep. Thank you. That sounds fantastic. You know, I'm happy to sleep anytime, anywhere someone wants me to. So here we go. This is the new chapter, chapter 24. We're going to talk for just a few minutes about this. I just want to get you started with the concepts, and then I'm going to have you do 1 or 2 Gauss's law problems for me, okay? So, if you think back to Physics 220, you're like, Physics 220, or whatever equivalent class you had, the first physics class with calculus, okay? Things probably started out with like motion. You dealt with things that were moving around, and then you talked about forces and determined like, hey, forces are making these things move. And once you got done with that, you might have started talking about energy, things like potential energy and kinetic energy, conservation of energy, and it was almost like a new way to do the exact same things. In fact, you probably discovered that like with things like projectiles, you were like, oh, I can use all these motion equations, or I can just say, hey, it has this much potential energy and this much kinetic energy, and I can quickly get to the answer a lot easier. And maybe some of you thought like, this is a lot better. Why did they teach me all that other stuff and make me do it that way? Okay? We're doing a similar thing now. We talked about forces. We talked about the electric field. Those two things are sort of tied up together as like one way to describe how some forces, some charges impact other charges. It was a way to describe that like positive charges will repel each other. Negative charges will repel each other. A positive and a negative will attract each other. And that's essentially what we spent the last two chapters analyzing in a very intensively mathematical way that kind of hurt a little bit. Agreed? And now you're going to have to do a lot of homework and practice a lot and go back and try to sort all that out and ask each other questions, ask me a lot of questions, send me a lot of emails. I have a button, it just replies LOL and archives it. Like I want to develop that just to mess with everybody, like lol and archive. I think that'd be fantastic. I could get in a lot of trouble that way, I think, especially if it's like department chair, lol and archive. Someone else, lol and archive, but no, I'm not going to do that. Ask questions as you delve into those two chapters. We're going to start thinking about a lot of the exact same things from the standpoint of energy. So you can see right at the top there, electric potential energy, okay? So here's the thing you need to remember. First of all, this electric force, you might remember the idea of conservative forces. Conservative forces, like they don't waste energy. In other words, when they do their work, they don't just throw energy away. So we have things like gravity, that's like gravity can have a potential energy. So like the pencil right now has gravitational potential energy. If I drop it, well, it loses its gravitational potential energy. But I can just pick it right back up again and get that energy back. It's not like it's just like gone forever and I can't get it back. On the other hand, something like friction, right? It's like, well, if I shove the iPad that way, it stopped because of friction doing work and essentially taking away the energy that I gave it. I gave it some energy. Friction said, I don't care about your energy. I'm going to stop this thing, suck all the energy out of it, and throw it away, and you can't have it again. Friction is non-conservative. It doesn't keep the energy around. If it were conservative, like gravity is, you might be like, push the thing this way, and then friction says, yeah, you can have it back. And that'd be a creepy world to live in, right? It doesn't work that way. How come it doesn't bother you when gravity does it? Gravity threw it back to me. Why doesn't that bother us, right? I threw it up in the air. I gave it some energy. Gravity said, I'm going to stop it. I'm going to stop it. I'm going to take away its energy. And then, oh, here, you can have the energy back. I'm going to push it back to you. It's a conservative force. It didn't waste any of the energy. Friction doesn't work that way. Boy, I wish I had a string right now attached to this so I could just be like, whoop, and pull it back. Friction just takes the energy and says, it's done. I did not conserve it. On the other hand, the electric force is a conservative force. It doesn't waste energy. If it does some work and takes energy away from something, it stores it as potential energy and can put it back into the charge. So conservative forces have potential energy associated with them, okay? So I have this force that is the electric force, and it's going to be connected to electric potential energy. And maybe you used U for potential energy, maybe you used PE whatever, it's all kind of the same. The electric force is associated with the electric potential energy. So if I were looking at the change, let's see, do I want to do it that way? I don't know. Do I? Yeah, let's do that. The change in potential energy, meaning the difference in potential energy, say, between two different points. It's equal to the negative of the work. This is like an equation you should have seen last semester. This is just in general for any potential energy. And we can use that equation and get some new stuff dealing with the electric force and the electric potential energy relatively quickly. Does anybody remember anything about work and what equation we have for it?
Force times distance.
It's basically a force times a distance. There's more complicated forms of that, but essentially it's force times distance. So in this particular case, I'm going to write it as an electric force, since that's the one that we're worried about, times some distance over which that force acts. So if I want to know how much work is being done by an electric force, well, the force is being applied to a charge, and that's happening as the charge moves a certain distance. Notice it's also equal to how much the potential energy of that charge changes as it goes from one point to another. And I can rewrite this one more time because we have an equation for the electric force. We can connect it back to the electric field. It's equal to QE. So we have that equation for both work and change in electric potential energy. So this is equal to work and the change in potential energy. So what do we mean by electric potential energy? In a way, it's not all that different from gravity. Okay? If I take a mass and put it in some gravity, right? Right now, it has gravitational potential energy because it's feeling the force of gravity and it could fall. Okay? If it starts at this point and gets pulled by the gravitational force downward, you might imagine as it's going lower and lower, well, that force is doing positive work on the mass and the amount of potential energy is decreasing until we get to the floor and there's no potential energy left because it can't fall any further. Okay? We have a similar sort of thing in an electric field. So again, this electric field concept, think of it like gravity. Like gravity is in existence in this region of space, and if I put a mass in gravity, it gets moved by the gravity. The electric field exists in this region of space, and if I put a positive charge in that electric field, it feels a force and gets moved. All right? So you can almost think of this region here, and I hate that this is so close together. In fact, let's draw it again ourselves. Let's imagine that there is an electric field that points like this, and it's being created because there are a bunch of positive charges up here, and there are a bunch of negative charges down here, creating this electric field in between that region of space. So that if I take a positive charge and put it all the way at the top, it can't go any higher in the electric field, it's going to have the most potential energy it can have. So here it has high electric potential energy. And of course, it's going to feel a force that repels it from those positive charges, and it pushes it in the same direction as the electric field. It's almost like it's falling, to relate it back to gravity again. But just keep in mind, I only oriented it like this to make it kind of like gravity, so that down was the direction it wants to go. I could tilt this at an angle, and then my charge would sort of fall along the electric field this way, I could make it go all the way upside down, and now my charge would fall up in the direction of the electric field. So in a way, like, gravity is a thing that exists, and we know how it works, but we don't have a lot of control over it. If I have something that's charged, and an electric field is something I can control, I can sort of make things move whatever direction I want them to. So it's like this powerful, fake sort of gravity, right? That I can make charges move the direction I want. So that means by the time the charge gets all the way down here, well, now it doesn't really have any potential energy left. We could say it has low electric potential energy. So as the positive charge follows the electric field, its amount of potential energy is dropping. Just like when the mass follows the gravity, right, and goes with the gravity, its amount of potential energy is dropping. Do you see the comparison between those two? Maybe a little bit, okay? Here, a positive charge falls in the direction of the electric field, has lots of potential energy when it's near other positive charges, and low potential energy when it sort of gets to the end of the line, when it's near the negative charges. Keep in mind, mass is just mass, right? Mass, there we go. Mass like attracts other mass. When I'm dealing with charges, I have positive and negative charges, which means I could do something like this. I could put a negative charge in here. If I put a negative charge here at the bottom, what can you say about its potential energy when it's at this location? It has high potential energy, right? Because it really wants to go this way. It can fall in this direction against the electric field. So we would say here a negative charge has high potential energy, electric potential energy. And once it gets done falling and reaches the other side where there's nowhere else left to go, then we would say it has low electric potential energy. So this whole thing is analogous to gravity, but in a lot of different ways. It's like more powerful, it's more versatile. We can do a whole lot more with it, and we have a lot more control over it with the technology that we have. Maybe one of these days we'll have artificial gravity so we can control it and just be like, I think all of us are feeling a little heavy today. We just like turn the knob down and we start to float out of our seats. That'd be kind of fun. Kind of scary, kind of fun. Maybe one of these days in the Star Trek universe that I'd very much like to live within. Sigh. One of these centuries. First, I need to live for a long time. So we need to reach the singularity, and then I need to plug my consciousness into a computer, and I don't know, things have turned sideways now. So it is 4:23. I'm not going to introduce a new topic. Instead, I'm going to draw a couple of pictures on a new slide for you. Hold on, I'm just thinking here. There's a lot of whiteboard space up here. As many of you as want to. Like, it would be easier for me to see your work and be like, what are you doing there? And like kind of point out what's going on and for you to ask questions. If you want to bring a group of 3 or 4 people and crowd around a little area of the whiteboard and work these problems, I think it's good for you and good for me and good for your awakeness, sort of in general, if you're not just sitting there being like, I don't know how to do this problem. I don't know how to do this problem. Instead, you're like up here kind of fighting with it with someone else, okay? So either find a spot on the whiteboard or mill about and find a group of 3 or 4 people and try these problems, okay? I'm gonna put one up here and then I will put the other one up in just a few minutes, all right? Oh, I had a page below. Let's see, what did I want to give you? Make sure I get it right. Let's see, we're going to have a conductor. It's going to be a sphere. That's not how you spell sphere. And it's going to be a thick shell, meaning it looks something like this. Whoa, like that. roughly. And then we're going to say that inside of that, there is a point charge. Okay? That is physically what's there. So I'm going to describe some different radii. I'm going to call this one R1 and this one R2. See if you can write an equation for E. So we'll say find E for R less than R1. Again, E for R in between those two. So we'll say less than R2 and greater than R1. And then E for R greater than R2. And if you're thinking like, oh no, this is an awful lot like what we did in class, it's going to be terrible, it's going to be a lot of work. It's a conductor, which means there's not charge densities to worry about. And I told you a little something about how charges will redistribute themselves, which means that you might be able to quickly get to an answer. And I tell you what, let's just do this one problem. We may start the next class by working another one. But find somebody to work with. I'm going to get at least part of this screen out of the way to open up more whiteboard space. Yeah.
What does it say next to sphere?
What does it say next to sphere?
Something shell.
Thick shell, meaning it's not just like a thin, completely hollow thing. It actually has a dimension. So we might say that like this is all solid conductor. Okay, that helps. It's a donut, if that helps at all. Look, markers, whiteboard space, like find a few friends and come try it. We won't watch. Nobody will watch. We won't be looking at you at any work. You can crowd around the four of you and completely conceal what you're doing. You are all, you have a whiteboard behind you. You should use it. This. I know you're like the second place today.